we were talking about analytical methodology for X-ray fluorescence. What I wanted to tell you is about the matrix effects. Usually absorption of X-rays from the atoms occurs well below the surface. The extent of attenuation depends upon the mass absorption coefficient of the medium and its composition. Usually signal decreases as the mass absorption component increases, the signal decreases, and sometimes enhancement of fluorescence may occur due to the secondary excitation of the analytical line signal. Suppose the secondary excitation takes place, then what happens? There are more electrons, more photons which will hit the detector, and these detectors will give you enhanced signal. So, but they are not the real X-ray fluorescence signals. So, you can minimize these effects by using closely matched standards except the added element analyte. So, you can take a look at some of the composition of the standards and then use those standards except the analyte element and then do the analysis using the standards. So, alternately you can use an internal standard that is introduced in all the standards and samples. So, one can also dilute the sample and standards that absorb X-rays only weakly. Water, organic solvents, starch, lithium carbonate, alumina, boric acid, borate glass, etc. All such things can be analyzed very easily, and here the matrix effect becomes essentially constant. So, the applications of X-ray fluorescence usually are occurring in different types of samples. When X-ray absorption and advancement effects are minimal, XRF line intensity and element concentration curves are linear. So, to get such linearity, NIST standards provide such materials, and National Institute of Standards and Testing. So, these standards are available, you can buy them from the market, which will closely resemble your samples, and they are all pre-analyzed. So, that you can have about 95% confidence in their analysis results, and when you get such analysis done, then you can if it matches your signal, then you can go for the actual analysis. So, such materials can be used to calibrate the instrument itself. Alternately, you can go for calibration as well as measurement. So, typical applications include the analysis of rock samples. There are about 22 elements that can be analyzed using XRF within a few minutes, and you can have alloy composition control during the manufacture. Supposing you are manufacturing some alloys in a furnace, then you have the raw material and then composition elements and then melt it, and then it will form a melt along with the slag floating on the top. What you can do is take a small amount of the melt, bring it to the laboratories. By the time you bring it, it solidifies, cool it, and then do the XRF analysis for composition of the alloys. And if the alloys composition is matching what you are planning, what is your production line, then you go ahead and take out the material and cast into different materials. Otherwise, if the analysis indicates that one or two elements or composing elements are not in the expected concentration, you can add the alloying elements and then rematch the standards and then cast it into different components once the composition of the melt is akin to your samples. And then you can determine lead and bromine in aviation fuels. This is an application where the liquid samples are analyzed. So, you can use calcium, barium, zinc in lubricating oils you can determine, and then pigments in paint samples also can be determined very easily. Another application is determination of chlorine, sulphides and sulfur dioxide using orthotoluidine, silver nitrate and sodium hydroxide impregnated micropore filter papers. What do we do actually is we take orthotoluidine, dip it in micropore filter papers and then expose it to the element. So, depending upon the amount of chlorine, it will give you some colored complex, and that micro filter itself we can insert as a sample in XRF and determine the chlorine. Same thing is true of silver nitrate for sulphides. Usually sulphides will react with silver nitrate to make them black, producing silver sulphide, and if you have the silver nitrate dipped micropore filter, you can expose it to the environment. If there is any hydrogen sulphide, it will react producing a dark spot where the silver halide, silver sulphide would be held in the matrix, and that sample can be straight away taken into the XRF. And then sodium hydroxide works for sodium sulfur dioxide. Sulfur dioxide dissolves in sodium hydroxide, and if you have a sodium hydroxide micropore filter, again you can expose it to the sulfur dioxide concentration and determine. Similarly, you can determine the concentration of elements in food articles. For example, iron, copper, zinc, etc., can be determined in rice samples. So, such things applications are also possible. So, in general what I can tell you is that the applications of X-rays are numerous, and the analysis is fast. You can complete the analysis within a few minutes, and then you can determine number of elements either sequentially or in simultaneously. Sequential analysis is useful for single elements, one after another you can go, and simultaneous X-ray fluorescence analysis require different design, and they are all almost always dedicated instruments. So, what are the advantages of XRF? We can summarize it like this: the spectra are relatively simple and not subject to much interference. This is one of the important advantages, because there are not much complications, and with a little training one can do the analysis. And then basically it is a non-destructive technique. So, you are not going to lose any sample. Therefore, they are useful for the analysis of paintings, paints in important paints, the paintings, you can analyze the paints, and archaeological specimens you can analyze jewelry, you can analyze antique items, etc. And then speed and convenience of the procedure is also one of the important advantages of XRF, and then precision and accuracy are comparable to established methods in classical techniques. This is very important, because in classical techniques the chemical analysis can match maximum ppm levels, not lower than that. So, in general XRF can be used for the analysis of such substances in ppm levels. Now, there are certain disadvantages also in XRF, and these disadvantages I can only summarize like this, that the concentration range varies from 0.01 to 100%, that is the analysis range, not lower than 0.01%. Sometimes it is not useful for light elements having atomic number less than 23. This point we have discussed already, And third disadvantage is it is the high cost of the instruments. Therefore, only when there are repetitive requirements and then multiple element analysis required, you should go for XRF. That should be the natural choice, and the concentration also should be very high. So, this completes our discussion on the X-ray fluorescence, and now we will switch on to atomic absorption spectrometry. We will move on to another technique, that is atomic absorption spectrometry. This is a very important technique for the analysis of number of elements, and the phenomenon of atomic absorption was first discovered in as early as 1802. It was Wollaston who discovered the phenomenon of atomic absorption in the spectrum of sunlight. Till then, it was thought to be sort of a solar spectrum was thought to be a sort of continuous spectrum, but Wollaston made a remarkable observation that the solar spectrum was in fact interrupted by number of dark lines, which was later confirmed by Fraunhofer in 1814. So, Fraunhofer re-examined this aspect, and then he confirmed that there were actually dark lines in the solar spectrum. However, the explanation for this came forward by Professor Brewster, and who put forward the idea that these dark lines in the solar spectrum denoted till then by usually alphabetical markers, alpha, beta, A, B, C, etc. they used to denote. But what he said is that these dark lines in the solar spectrum are in fact due to the presence of vapors of certain elements in the sun's atmosphere. A very important observation, because it related to the absorption of solar radiation by these vapors. Therefore, it follows that the substances emitting radiations, specific radiations, are also capable of absorbing the same radiations, causing the spectrum of dark lines in the bright background. If there was no absorption, the emission would be a very fine continuous spectrum, and there should not be any dark lines at all. So, if there are certain elements in the sun's core or atmosphere or corona or somewhere, these elements are absorbing part of the radiations, and then when they absorb the radiations, the emission intensity becomes less. So, this is due to atomic absorption, because at the temperatures prevailing in the sun's atmosphere, there cannot be any molecules, but only the atoms. So, this phenomenon is generally known as Kirchhoff's law. It was used to deduce the presence of oxygen, hydrogen, sodium, iron, calcium, etc. in the solar spectrum. This is how we came to know that oxygen, hydrogen, sodium, iron, calcium, etc. are present in the solar atmosphere. The experimental confirmation for this came from the electric arc or spark, when the spectral source surrounded by atomic vapors also showed similar dark lines because of the absorption of the emitted radiations. So, the same kind of temperatures prevailing in the solar atmosphere were generated by the arc or spark on the earth, and when the generation of the spark was using the electrodes, and if the electrodes contained particular elements, the same spectrum of the arc showed dark lines. Then they thought, oh yes, it must be due to the same element, and if we can match the frequency of the elements absorption, then we should be able to determine the elements even in the sun. So, that was the thinking. So, because of the absorption of the emitted lines, the vapors also showed dark lines in the arc or spark spectrum. So, this absorption leading to the decrease in the intensity of the emitted radiation was also demonstrated by Foucault in France. He showed the reversal of the spectral lines. So, in essence what we are looking at is that the sum of the elements in the sun are absorbing the same radiations that are present in the emission of the same elements. So, here this is the these are known as Fraunhofer lines, and here you can see the dark lines in the colored spectrum at the bottom. Here I have put wavelength, this is 4500, 5500, 6500 like that up to 9500. Here we have number of spectra, and these spectra correspond to the dark lines which are matched by the different kinds of elements. So, this is a very interesting observation which correlates the atomic absorption to the elements present in the sun. This is actually a detailed diagram of the same, where you can see that the elements determined using these dark lines. You can see dark lines all over this. One is blue, and then it is green, and then it is orange, red, etc. And here you can see that potassium, hydrogen, and then calcium, cobalt, this is cobalt, and then iron lines are there, hydrogen, then magnesium, then there is sodium and oxygen and water vapor. All these elements all these molecules and elements are there in the solar spectrum. So, it is a very interesting and confirming factor that the atomic absorption phenomenon, even though known as early as 1800s, is known to the scientists, but it was not repeated. It was the significance of it was not known. So, in 1902 Wood repeated the experiments of Kirchhoff and Foucault, and he proved conclusively that what he did is he introduced sodium vapor in the optical path of sodium emission lines, and then what he noticed was a reduction in the intensity of the emitted radiation. Very conclusive proof. You take the sodium light, what you see in the street lights, yellow bulbs which emanate radiation in yellow color, they correspond to 589 and 589.6 nanometers. It is a doublet, two types of wavelengths are coming, both of them are yellow light only. And if you take that radiation, introduce sodium vapor in the optical path and measure the radiation intensity. We know how to measure the radiation intensity by photomultiplier tubes and other things. We have studied those things in our atomic absorption studies, molecular absorbance, photoluminescence, etc. If you do that, you will see a reduction in the intensity of the emitted radiation. That is, before introduction of the sodium vapor, you get certain intensity, and you introduce the sodium vapor will absorb part of the radiation, and the outcoming radiation will always be having lower intensity than the incident radiation. So, by analogy with acoustic resonance lines, he also showed the possibility of using these resonance lines to detect traces of mercury. He extended the analogy to mercury. Suppose I have a mercury lamp, then I introduce mercury vapor. Mercury vapor will generate mercury atoms, and these mercury atoms will absorb part of the radiation. So, if such a thing is actually happening, we should be able to determine mercury in different kinds of samples. That was the logic. So, he also showed the potential of this technique, but it was not recognized by analytical scientists and spectroscopists till 1924. Then only the thinking started that yes, we can use such a phenomenon for using these radiations, atomic absorption phenomena, to determine sodium, mercury, etc. Somewhere around that time, around 1930, 25s and 30s, Angerer and Jose published the atomic spectra of all iron group metals. So, now we know at what frequency iron atoms emit the radiations as well as absorb the radiation. It is like a dictionary. So, a database. So, this was followed by, he did it for iron group metals, and then Frein and Smita published the similar database spectrum for indium, aluminum, gallium and tantalum. So, Müller and Pringsheim in 1930 published the first atomic absorption method of measuring the mercury content in air. You will be surprised to know that the concentration of mercury determined in 1930 was of the order of few ppb, parts per billion, which we are doing now, but first time it was demonstrated that you could do ppb level analysis of mercury in air in 1930s. Even this did not evoke much interest in the analytical chemists for the determination of other elements, because mercury, we know that when it falls on the floor, the mercury vapor is automatically generated. So, if you just have a mercury source and a detector and put some mercury in the optical path, it will always show some amount of absorption, and that could be determined. But for generating the atoms of other elements, that was the big challenge, and that is why atomic absorption did not take off as a real technique till late in 1955s. In 1955, Walsh developed the first real application of atomic absorption to chemical analysis. In the same year, Alcamade and Mietz described a double beam method of spectral selection with two flames, one for excitation, another for absorption. The first being the source of atoms and the second as the atomizer. Since then, the atomic absorption spectrometry is in the forefront of chemical analysis. The first commercial atomic absorption instruments appeared in the 60s due to the efforts of Alan Walsh in 1955, and subsequently commercial instruments appeared in the 1960s. But then a revolution took place in the analytical front. Spectacular advances in instrumentation, electronics, and then automation and computers over all these years since last 5 decades have made atomic absorption spectrometry one of the most really reliable analytical techniques of modern times. It is perhaps equalled only by atomic emission spectrometry, which also has been developed only since last 20 years. But atomic absorption and atomic emission, both these techniques are of recent origin. Atomic emission is slightly recent, but atomic absorption and atomic emission, both of them hold the pride of place and first choice for the analysis of a number of elements in terms of sensitivity, simplicity, specificity and the speed of operation. Today, the first choice of any analytical scientist, if you ask him to do a chemical analysis, first he will say, yes sir, I will do the atomic absorption method to determine the elements. So, it has come up to this state only because of the advances in instrumentation, electronics, automation and computers. And the development of electrothermal atomization was the next big leap for the detection limits, for increasing decreasing detection limits of the order of few ppb, parts per billion, and sometimes even picograms, sometimes even femtograms, that is 10 raised to minus 15 grams of the substance can be detected only by the development of an accessory known as electrothermal atomization. And this was spearheaded by Professor Labov of Russia, and Professor Massman developed the equipment to achieve electrothermal atomization. And he pushed the detection limits of atomic absorption technique to nanogram levels, picogram levels and femtograms levels. And other accessories for atomic absorption which have developed over the years include hydride generation. So, a hydride generation atomic absorption spectrometry is useful for the analysis of arsenic, antimony, bismuth, selenium, tellurium, germanium, lead, etc. These are 6 or 7 elements which form hydrides, and this hydride generation atomic absorption spectrometry permits the determination of picogram levels of these elements: arsenic, antimony, bismuth, selenium, tellurium, germanium, lead and mercury also to some extent. And you will appreciate that all these elements, arsenic, antimony, bismuth, selenium, tellurium, germanium, lead, etc., they are all environmentally very important elements, and we have strict standards for their presence in the environment, and the standards refer to parts per billion level of existence in the air and water environment around us. So, atomic absorption spectrophotometry using hydride generation atomic absorption works for these elements. And cold vapor, mercury vapor, cold mercury, what was described in 1920s, that I had explained to you just now, the cold mercury vapor determination, it is useful for picogram levels of atomic determination of mercury, especially to make it the first choice of analytical chemists throughout the world. So, these are the variants of atomic absorption, and you can gauge the popularity of the atomic absorption spectrometry by the fact that more than 100 books have been published only on atomic absorption spectrometry, and there are more than 10,000 research publications only in this area, and 5,000 symposia and conferences, including national, international conferences till date have happened, and these symposia and conferences and publications most of them deal with atomic absorption analysis in a variety of matrices, where biological, chemical, nuclear industry, industrial products, soil analysis, environmental analysis and several other applications where atomic absorption takes the leading role in deciding which of the technique that can be utilized for the chemical analysis. So, now what we would like to do is, I would like to give you some sort of an small introduction to the theoretical principles of atomic absorption. Sometimes this may be slightly more involved and more mathematical, but really do not worry, because all the theoretical considerations what we are going to have discuss involve the applications of a subsequent development of the instrument, and they are not really very rigorous in derivation, but to some extent they are, because the atomic absorption spectrometry has been put on a very firm foundation, since it is the preferred elemental technique, and it may be slightly complicated, but I will try to make it as simple for you as possible. And the basic ideas which have been developed using these theoretical aspects are put into operation into the instrumental design and the chemical analysis, etc. So, if you feel slightly overwhelmed by the derivation, etc., what I suggest is you take a look at it leisurely and then go through this lecture, and also you can go through other textbooks which will clarify your ideas, because in general at the first hearing you may feel slightly overwhelmed by the derivations, especially the concepts, and I will try to make it as simple as for you as possible. So, the simplest concept of atomic structure is that of the positively charged nucleus containing protons and neutrons. These are surrounded by an equal number of electrons orbiting in space. This we have discussed number of times, how is an atomic structure is built, and according to quantum mechanics, such a system can exist in a stable state only if its energy is quantized, and at the lowest level as well as in the excited levels. So, all other levels except the ground state are referred as excited levels, which can be induced to be occupied by the electrons to go to next higher energy level or excited levels by mechanical or electromagnetic means. Mechanically, you can heat the substance and then produce the atoms, which will get excited and go to the next higher energy level. Also, you can use electromagnetic radiation, make them fall on the atomic vapor and then excite the atoms. These are the things which we have discussed earlier with respect to molecules in spectrophotometry, but essentially the same discussion is taking place now. Only thing is, we are talking of the atoms now, not the molecules. So, the energies associated with these atomic states are in the range of few electron volts, represented by Gaussian diagram. Such a diagram for sodium I am showing in the next slide. You can see here the energy level diagram for sodium. So, I have here the 3s energy state in the bottom, and then here it is 2s 1 by 2, that is the excited state, 2p 1 by 2, 2p 3 by 2, 2d 3 by 2, 2d 5 by 2, 2f 5 by 2, 2f 7 by 2. So, here are 3s, 4s, 5s etcetera. The energy excited energies are shown here by simple lines, and here you can see that the electrons, the excited states are populated nearer and nearer in 2 p 1 by 2 and 2 p 3 by 2 etcetera. And the axis here is the ground state electronic levels, and on the abscissa it is electronic volts. So, what is happening here is we are determining, taking the sodium atom and determining its energy level. For example, 3s is occurring approximately at 0 electric volts, 0 e volts. So, most of the electrons in the ground state are having energy of the ground state approximately 0, and then I have 1, 2, 3, 4, 5 electron volts. That means, I am exciting the atoms by applying 1 volt, 2 volt, 3 volts, 4 electronic volts and 5 electronic volts, and the electrons will be excited from here to the higher energy states described by 2s by 2, 2 p by 2, 2 p 3 by 2 etcetera. So, the excitation can occur here like this from 3s to 2 p 1 by 2, and this occurs around 268 nanometers. Next line is this line excitation, and this occurs 285.3 nanometers, and 4 p level occurs at 330.3 nanometers, and then 330.2 also there is one, and 3 p there is 589 nanometers, and another 3 p occurs at 330.3 nanometers. So, like that you can see that most of the excitations are starting from the ground state to higher energy states up to this, and then here, and then 4 p state, 3 d state etcetera, 4 f state also, and all these transitions are coming back to 3 p and then falling back, because they are, I am showing all of them as reversible reactions. That means, an excited electron can also fall back to the ground state. Either it can fall back from the same level to which it is excited, or it may be excited somewhere else, some other line, but it will fall back to 3 p, and then from there it can fall down. So, I have shown here dark lines, 2 dark lines at 3 p levels and 2 dark lines at 4 p levels. So, these dark lines represent what is known as resonance energy. That means, it is the lowest energy to which an electron can get excited up to this, and then it can come back to the ground state. So, the lowest is 3 p, next lowest is 4 p. So, these are known as resonance lines. So, this is the energy level diagram of sodium. This I have shown you even in when I was talking about atomic fluorescence, similar diagram, and I had made a statement that most of the elements, the energy level diagrams are represented like this only. And if you go back and check, I had shown you the spectra for magnesium, lithium, cobalt etcetera. So, what we are looking at it is right now our interest is in the dark lines that are taking representing the transition from ground state to the next higher energy state, that is 3 p and 4 p. All others are non-resonance lines. That means, the excitation and emission does not occur at the same wavelength, and that is not the minimum. So, if we use the minimum excitation, then we should be able to determine what is the requirement of the electromagnetic radiation to excite an electron from the ground state to the next higher energy state. So, this can be calculated in terms of electronic volts or in terms of radiation of particular wavelength. So, we are here, it is very simple now to know that emission of light occurs when an atom reverts to a state of lower energy. First the element has to excite, go to next higher energy state, and it has to return to the ground state, and that time emission can occur. This we know it as fluorescence or atomic emission. So, Bohr's equation expresses the conservation of energy by the relation E is equal to h mu. So, suppose I have E1 state, another state is E2, from E1 and E2 if there are two states, one correspond to E1, another corresponding to E2, I have an electron here, it can go like this, and the excited electron can come back like this. E1 is equal to h mu or delta E can be h mu and E1 is equal to h mu 1 and del E2 is equal to h mu 2. So, the difference delta E is difference between E2 minus E1, and if you put h mu 2 minus h mu 1, you can derive that you can take out the difference h into mu 2 minus mu 1 and h, you know that it is something to do with the energy, and E1 minus E2 goes to mu and h. So, the wavelength can be simply calculated using this simple formula, lambda is equal to c by v, c by mu, which correspond to h c into E1 minus E2. So, where c is the velocity of light, h is the Planck's constant, all this we have discussed earlier, and v is the mu is the frequency, lambda is the wavelength, E1 and E2 are the energy levels of the excited and ground states. Now, inserting the numerical values of h, pi and other things etcetera, we can calculate what is the wavelength of the emission, that works out to some particular number 1.23978 divided by the energy difference between the ground and excited state, that is E1 and E2. So, a transition from the resonance level of sodium to the ground state, we can go back to this figure from the ground state for sodium up to 3p, we can calculate. So, that works if I use all these constants and it occurs at 2.102 electron volts, and if I insert those values I get 0.5986 micrometers or 589.6 nanometers. So, it is like this I can calculate the energy level or wavelength for each element. Any element I know if I know the difference between the two energy states. So, when a photon of energy frequency mu interacts with an atomic energy atom of energy E2, the atom may be able to absorb the photon also, thus raising its energy to E2 plus h mu, provided the new energy level is equal to one of the excited energy level of that atom. In the case of sodium, we know that it is p atoms, p orbitals. So, we can write like this, a very simple same thing what we have written earlier, comparisons of equation 1 and 2, this is for absorption. Now, we are talking about absorption, earlier equation 1 refers to emission. So, it shows that comparing these two expressions, this one and the previous expression, this one expression, we know that the atom may be able to absorb the photon, and an atom can only absorb the photons that it is able to emit, because the energy levels are fixed. So, it can either absorb if the atom is in the ground state. If the atom is in the excited state, it can emit, but the radiation that it emits corresponds to the same energy level difference between the two. This forms the basis of atomic absorption spectrometry. So, the fundamental difference between emission spectrometry and absorption spectrometry, we can define it like this. For emission to occur, a number of atoms must be in the excited state, higher level, and then only when the excited atoms come back to the ground state, the energy will be released, and it may be in the form of emission. Now, for atomic absorption to occur, where should the number of atoms should be? They should be in the ground state, so that they can absorb the radiation and go to higher energy level. So, this second condition is easily attained compared to the former, that is to have atoms in the ground state is more simpler than having atoms in the excited state. It is very simple logic. Basically, when you do not do anything, most of the atoms are in the ground state, and to have more number of atoms in the excited state, you have to supply energy. So, without supplying the energy, it is possible to have the atoms in the maximum number of atoms in the ground state. So, the second condition is easily attained compared to the former, in that free atoms in the ground state can be easily generated. We can generate the free atoms. How do we generate the free atoms in the ground state? We will see later. But if you are able to, if you have a choice between generating the atoms in the ground state or in the excited state, the one which wins favor immediately is the ground state. So, in the ground state it is easier, and we can produce atoms just by heating in a flame. So, compared to the excited state, and that is what it means essentially. So, the characteristic absorption wavelength of an atom, I have already demonstrated for sodium, that we can calculate the wavelengths and determine at what wavelength an element can absorb the radiation. So, once the energy levels are experimentally determined, we can determine the wavelength of absorption also, because both of them mean the same. But several wavelengths are never observed. Even though you are able to calculate, many of the wavelengths you do not see in the emission spectrum or in the absorption spectrum. That is because some sort of selection rules are there, which will permit only certain transitions, and those transitions are seen in the emission spectrum or in the absorption spectrum. Some of them are not permitted because they do not satisfy the quantum mechanical requirements rules, and these rules were evolved empirically first and then subsequently confirmed by quantum mechanical calculations to the concept of transition probabilities. So, if the transition probability, if the quantum mechanical calculations permit a particular transition, the probability is more. but if the quantum mechanical calculation does not permit, the probability of a transition is always less. That is how both of them are complementary to each other. Quantum mechanical calculations have to be supported by the probability and vice versa also. So, the probability of a spontaneous emission by transition between two energy levels E 1 and E 2 is how do you define? It is defined as the fraction of number of atoms that drop to lower energy level per unit time. Of course, if you are talking about the probability, distribution, rate, etc., we have no other recourse except to resort to equations and mathematical expressions. So, the probability can be expressed as like this, as an equation like this. I have written here d n 1 is to 2, level 1 to level 2, the probability rate of transition is denoted by a proportionality constant and number of atoms n 1 present at n 1. So, from n 1 they are going to n 2, and that is the transition per unit time. So, A is the coefficient here in this equation 3, A is the coefficient of proportionality. This is known as Einstein emission coefficient. So, higher the probability of transition, the greater is the intensity of emission. The strongest emission lines correspond to values of A in the range of about 10 raised to 8 to 10 raised to 9 per second. And the another aspect, that is absorption. Similarly, if I have n 2 atoms in the lower transition state, they are irradiated by a radiation of frequency mu derived from equation 1, and the volume flux density rho v is the number of d n 2 to n 1 state that will absorb the radiation in the time fraction dt. It should be proportional to the number of atoms in the high excited state n 2, rho v and dt. So, mathematically I can express this as d n 2 to 1 going to b 2 to 1, this is the proportionality constant n 2 and rho v and dt, that rho v represents the volume flux density of the transitions. So, now we will have to define the B 2 to 1, this transition has to be different from Einstein emission coefficient, because now the emission is not occurring, but absorption is occurring. So, we define this as Einstein's absorption coefficient. Nowadays, we do not use the Einstein absorption coefficient etcetera, but we simply term it as oscillator strength. That is, it is being used to denote the relationship between the B and the total number of electrons. So, what we mean actually in this case is that the electron is going from one state to another state. I have two states. This is an electron and it is going to the next energy state. It can't remain there forever. So, it has to from here it can come back to ground state. So, the electron is occurring is going from ground to excited to ground state like this, and then that means it is going according to a fixed plan like an oscillator. It either goes from here, from this point to the higher energy state and higher energy state to ground state, and that one is known as oscillator. That means, it is oscillating only between the two possibilities. So, it is known as harmonic oscillator, because the oscillations are reproducible, because the energy levels are fixed. So, the electron also has to go only between those two energy levels. So, in this equation we can say that the B2 to 1 transition is nothing but the Einstein absorption coefficient can be determined by pi e square lambda wavelength, and another is the mass. Other things are all known, H c and F2 to 1 is the probability. Therefore, for sodium D lines, the oscillator strength is 0.23 and 0.47. You remember there were two lines excitation, lines of excitation from S to P. So, for potassium they are 0.35 and 0.7. Similarly, for different elements their numbers will be different. So, the emission lifetime of any transition is approximately 10 raised to minus 8 seconds. This we have seen in our discussion even in molecular spectrophotometry. However, if there are sufficient number of atoms are present, steady state emission or absorption phenomena can be observed within the experimental time frame. So, what I want to tell you at this stage is if there are sufficient numbers of atoms, steady state absorption emission, absorption emission, emission absorption. So, the number of atoms that get excited to higher energy levels equals the number of atoms getting de-excited to lower energy levels. That means, same number of atoms will be there in the excited and ground states. So, for atomic absorption to occur, what we need is intense emission of the desired element must be generated first. The radiations generated from electric dipole, magnetic dipole, electrical dipole give rise to such lines, which among which electric dipoles are most important. Both Einstein emission and absorption coefficients must be non-zero only if the levels involved are of opposite parity and if delta j is equal to plus or minus 1. That means, the selection rules should permit total quantitation. Now, we will continue our discussion in the next class. At this stage, we only have to understand that the number of elements must be more in the ground state.